Could we go over nested classes from Ethan? Yes, we can. I will do that first. Okay. So I'm gonna go ahead and share my screen. All right, would somebody tell me if they can uh somebody tell me if they can see my screen, what's going on? Is everybody on mute? Like,
Oh yeah, I can see your screen.
okay, good, because all right, cool.
Yeah, it's the vector H.
Yes, perfect. So somebody's first question was, can we go over nested classes? Which we actually will be kind of like, that is a pertinent question to this review. So whoever asked it, good on you. You're making this review move a lot more efficiently. So specifically in y'all's first assignment, I hope y'all have started by now. We've got an outer class and an inner class. So as you can see, we've got the outer class, which is vector, and then the inner class, which is iterator. It's a little bit tricky how they split up the declaration and the definition. In C++, these are actually two different things. So as you can see right here, this is a class declaration. So it's like saying we've got some kind of class iterator, but the definition actually doesn't happen until later, which typically you would see this kind of behavior split up between a .h and a .cpp file. So you'd have somewhere in the .h, you'd have like class iterator, and then you might like define it elsewhere. But because everything here is happening in the .h file, it's a little bit goofy, if you ask me, honestly. But essentially, all that's happening when you have a nested class is you are defining this class within the scope of the outer class. So this class right here, this inner class, all of these variables are scoped within two classes. So this is scoped like inside a class, inside a class. And that is like, maybe not something that y'all have seen before. I made a point to see, it's this one. So these are all the code examples I'm going to go through today. I made a point to show y'all the scoping operator specifically to address this question. So again, whoever asked if we can go over nested classes, that's a great question because that's actually the first thing I was gonna jump into. So as you can see, in this example, we've got the outer class, which is vector, and then the inner class, which is iterator. And in order to reference members or functions or methods from inside a class that's nested, you have to use what is known as the scoping operator, which looks like this. So in this example that I'm providing you here, basically I just wanted to show you how you can use an iterator to traverse an array in the exact same way that you can use like an index to traverse an array, or in this case, a vector. And let's see. So what's not shown here is specifically this STD right here. So sorry if this is like a lot to take in all at once, but basically, if you want to access a member of an inner class from within an outer class, you use two colons, which is known as the scoping operator. And then as you can see, so we start with STD, and then within the scope of STD, we scope into the vector class. And then within the vector class, we scope into const iterator class. So this is similar to y'all's PA, in which you've got an inner class, which in this case is const iterator, which is scoped inside the vector class. So in y'all's example, we've got const iterator and vector with a lowercase. In y'all's example, that would be referencing something vector with an uppercase, and then just iterator right here, if that makes sense. So I mean, it's like, imagine like you've got an array here, which is a private member. You've got a class, which is a private member. You define functions inside a class. You define other classes inside a class. It's nothing that would blow your head off entirely. I hope that adds some clarity. If anyone has any questions, please unmute yourself and interrupt me, because I would love to answer them. So anyways, the first thing I wanted to show y'all today is I've gotten a lot of questions in lab, like, what are iterators? What do they do? Why would we even use an iterator? And that's a great question, which I feel like unfortunately is not answered very well during the vector assignment, because vectors can be traversed with indices, right? So in this example, we're creating a vector int my vector, we're giving it a list that we initialize it to. we can iterate without the use of an iterator pretty easily for a vector, right? So we've got for int I is equal to 0, and you basically increase this index until you get to the size of the vector. And then you here in this example, I'm just printing what's at the vector. The point that I want to make with this code example is that these all three for loops in here have the exact same output. So you could iterate with an index across something like a vector, or you can iterate with an iterator. So in this instance, for a for loop, you've got your declaration and then your condition and then your increment. Same thing with this for loop. So we're creating an iterator. I know that this is kind of like a monstrous line of code. So apologies if it's a lot to take in all at once. And then this is your condition. And then at the end, you've got your increment. And then we're going to be dereferencing the iterator at each step. So within y'all's PA1, when you define the .begin function for your vector and it returns an iterator, this is why you need to define what that is, because there's going to be an instance where if you want to create an iterator in a for loop and then be able to iterate using that iterator, you're going to have to be able to call .begin on a vector. Same thing here when y'all are defining the not equals operator in PA1. What you're doing is that there is a case, like for instance in a for loop, where you actually do need to compare the truth value of two iterators. That might be kind of abstract when you receive the assignment, like why would I ever need to compare if two iterators are the same? Well, this is your example right here, because you have an iterator to the first element, and then you're increasing that iterator until you get to the last element, and then you're dereferencing the iterator. So all of these operations like star iter, vector.end, iter plus plus, these all correspond to things that you would see in vector.h. So for instance, iterator plus plus, you have to define it here. Dereferencing an iterator, you have to define it here. Not equals, you define it here. So because I'm using the standard library, I'm using the iterators that are already built into the vector class, like the C++ vector class. So this has already been done behind the scenes. And if I go ahead and compile, I think I called this what? Iterator.cpp. You can see I can run the output and it gives me three lists that are all exactly the same, right? So I define the vector to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, boom, good. Let's see. Also, I wanted to make a point down here. If y'all haven't seen this auto keyword yet, just to get familiar with it, basically this auto keyword is an automatic typing, it's an automatic typing ability in C++, where if you have an assignment statement like iter is equal to myvec.begin, whatever the return type, whatever data type you get from this assign statement will automatically be generated here. So for instance, I just happen to know that I've got a vector of int type and I'm trying to get the constant iterator class. But if you don't want to type all this garbage and you know that you're going to be having an iterator that is returned from this function, you can just say auto iter is equal to myvec.begin, and it's the exact same. And then for the second example I have, so again, sorry if I'm going at the speed of light. If it feels like I'm going too fast, I am going too fast. It's not your fault, it's mine, I promise. I have defined a second little example right here, which kind of shows you where an iterator would be useful. So when you have a vector, the vector is stored in contiguous memory, or at least the array inside the vector is. So you can do vector at 1, vector at 2, vector at 3, and then traverse that way. But if you have a data structure that is not contiguous, something like a linked list, you all have seen linked lists before, the way that you iterate through that list is now more challenging, because if you have a pointer to the first element, and let's say you want to find the fourth element, well, you can't just do this pointer plus 4, right? You can't just do arithmetic, because technically all of these entries in this linked list could be stored in different places in memory. You have no idea. So you can jump from this one to this one and from this one to this one. But if you want to do math, like to iterate across every element, that is like something that the iterator class will do for you. So I've defined this templated function, and again, don't freak out. Basically, this templated function takes a type of data structure. So in this case, it'll be either vector or list. And then taking that list, it has an iterator. So you're calling, and this is another example of where auto is useful. So you're calling the container, which in one case will be a vector. So you'll have a vector iterator here for one case. In another case, it'll be a list. So you'll have a list iterator in this case. And then you start with the first iterator, go until you reach the last iterator, increment that iterator, and then dereference it. And the point that I'm trying to make here is that even though you have two different data structures, you're going to get the same output because specifically the iterator class handles all of the nasty pointer math that needs to happen behind the scenes. And as you can see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And this would work across any data structure, right? So if you had something super complicated like a map, which I didn't really want to scare y'all off with maps. I don't think you'll even see an ordered map by the end of this class. It would still be the same idea, same principle. So you can take any data structure that has an iterator built in, and then instead of worrying about how do I get from one element to the next element, it's all done for you because these functions have been defined already, if that makes sense. So I hope I answered the first student's question about specifically nested classes. I hope I reviewed some stuff about iterators. And if y'all are still unclear on iterators, Andrew is another TA, made this wonderful PowerPoint right here. Like this stuff is great. This is actually gold. So I don't want to go through it, but it's linked on Canvas and the announcements. Y'all should definitely go check this out.
I do have one question. Like it took me a while to just figure it out for the homework, but like without giving anything away, just I was confused why subtracting iterators gives you a size underscore t value.
Okay, that's another excellent question. So sorry, I've got like all these Zoom wizards. Uno momento, por favor. Okay, so in the starter code that they give you for PA1, you're asking why I know what you're talking about. It's somewhere
Yeah.
in let me find the example. Okay, well here's an example. So what is size t and why is it the data type for your capacity and your size? Size t specifically it's similar to an int or a double type. It's just semantically, whenever you see size t, you know that you are referencing an index in a data structure. So specifically, a size t could do anything that an int could do, right? So you can have like size t plus size t, or integers can do multiplication, division, subtraction, any operation. It's just semantically when you see size t, you know that you're talking about, yeah, like this is what you're talking about. Like you know that you're talking about the specifically the size of a data structure or indexing a data structure. So don't freak out. These work exactly the same way that ints and doubles work. So just know that. I mean, I guess not doubles because there wouldn't be a decimal point that you would need, I don't think. But yeah, specifically, I think, and don't quote me on this, I think it's most comparable to an unsigned integer. But yeah, it's just semantic benefit mostly. And y'all might have instances in which you define a function with an iterator and a size t, and you can't pass an int in here, even though you'd like to, right? Like imagine you wanted to insert like, int 4 count here, and then it doesn't let you, just retype it as a size t. It shouldn't bite you. But that's a great question. I wish I was more prepared to answer it, but I think that's at least the basics. Okay, so first PowerPoint we're going to be reviewing today is Big O. So y'all have seen Big O already, hopefully. In lecture, it's basically a way of classifying the asymptotic behavior of an algorithm as far as time complexity goes, right? So you can kind of group different algorithms by their complexity by order of magnitude, right? So this chart does a really good example. Like this is a good example of showing you the different groupings of orders of magnitude. So obviously the lowest order of magnitude is constant time, and then you've got log time, linear times log time, quadratic, cubic, exponential, factorial, and so on and so forth. And basically, as you're moving up this chart, you're saying that as n approaches infinity, the behavior of this algorithm gets worse and worse and worse and worse. And part of what you're going to be learning in this class is that there are sometimes different time complexity options for accomplishing the same task, right? So for instance, if you want to sort a list of integers, there are some algorithms that can do it in factorial time. There are some algorithms that can do it in quadratic time. There are some algorithms that can do it in n log n time. And then there's nothing faster than that, if that makes sense. So examples would be like BOGO sort. Y'all don't need to know what that is, but if anyone wants to do some rabbit hole digging, look up BOGO sort. That's a factorial sorting algorithm. It's terrible. It's absolutely the worst. Quadratic sorting we're going to be covering today would be like bubble sort, selection sort, insertion sort. And then n log n sorting would be like merge sort, quick sort, which y'all haven't learned yet, so don't freak out. But basically, you're going to get, by the end of this class, you're going to get very comfortable with looking at an algorithm and deciding this is the time complexity order of magnitude, this is the time complexity order of magnitude, so on and so forth. So let's see. There are some whoever the guy who designed these slides, Nihar, I don't know if y'all have met this guy, he's wicked smart. There's definitely way too much information on here. So if any of y'all are as smart as he is, you can look back at this stuff and actually derive things for yourself. But for the purpose of today, I'm going to be going through some examples. So this is a basic example, right? So we've got some integer n, and that, as in when you see n on this diagram right here, that's referencing like the input to the algorithm. So if we're talking about searching on an array of n integers and we say that a linear search is O of n, well, then what we're saying is that the time complexity scales with the size of the input, if that makes sense. So for this example, he was very explicit and said int n, and then we're looping until we get to n. So we're starting at I equals 0, and then we're looping until I equals n. And this is a very explicit way of showing what it looks like to have a big O notation of O of n, right? Obviously, because this loop is going to happen once for each whole number from 0 to n, and obviously therefore it's O of n. And as far as the runtime goes, different people calculate this in different ways. This is kind of iffy, but I think specifically what's happening here is that the +1 comes from this allocation. So you're no, it wouldn't be this one. This is a definition. So you would be allocating here. You'd be allocating count is equal to 0. So because that's like an assignment / like memory statement, that's your +1. And then for this loop right here, I think he's counting all of the operations to update the for loop. So that's 1. And then the count is being incremented. So 2 operations per loop, and then there's n loops. So therefore 2n + 1. Don't buy into this too much, I don't think, just yet. What's really important is that you'll understand that this is big O of n. Okay, so let's see, next example. This is an example of a quadratic algorithm, even though it's kind of tricky to see that it is that way. So you might have, instead of 1 input to an algorithm, you have 2 inputs. So in this case, you're looping from 0 to n, and then also you're looping from 0 to m. And for n iterations of this outer loop, you're iterating from 0 to m. So 0 to m happens n times, therefore, mn. This is the same time complexity relatively as O of n squared. It's just instead of having n in the outer loop and n in the inner loop, you've got m and n, which break it up, which there's not really a difference, assuming that m and n are relatively the same size. This is just a more explicit way of saying what I just said. So if you've got 1 input instead of 2, and then you loop on the outer loop to n and then the inner loop to n, obviously it's still O of n squared. This one, there's a little detail. So if you like really squint your eyes, you can see that instead of looping from 0 to n and from 0 to n, in this case, you're actually ending at j is equal to I. So what that would look like is that imagine n was 4, you're going to loop 1, 2, 1, 2, 0, 1, 2, 3, right? Because I guess 4 wouldn't be counted. And then in this inner loop, you're going to loop 0, 1, 2, 3, and then the next iteration is going to be no, in the first one it'll just be 0, and then 0, 1, 0, 1, 2, 0, 1, 2, 3, and so on and so forth. If you basically imagine, I'm going to go back to this example right here. If you basically imagine these time complexities as geometric spaces, which I think is totally valid, then linear time, you can imagine it as a line, and quadratic time, you can imagine it as a plane. So without like starting to sound like schizophrenic or anything, you can kind of make sense of this type of algorithm. So, obviously it's on the order of O of n squared. So we can visualize it somehow as if it's like a graph or a plane. And if each iteration, the line that we have to iterate get smaller and smaller. This is kind of like a triangle. So at the next weekend review, I'm going to have a better proof of this. This is a little bit too advanced for now, but this is a formula that I would memorize if I were y'all. This is whenever you see a loop, and then the inner loop terminates, depending on the range of the outer loop, you're going to have this time complexity. And next week in review, I'll probably show y'all a proof for such. Let's see. So this is what it looks like to have log of n running time. Basically, whenever the sentinel value, so in this case, the sentinel value is also n, whenever the sentinel value, or the value that tracks the progress of the loop, is decreased or increased with multiplication or division instead of addition or subtraction, then you have logarithmic time, which in this case, what we have to figure out is how many times can we divide n by 5, and that's how many times the while loop will run. And how many times you can divide n by 5 is similar to asking how many times can you multiply something by 5 to get n. And so obviously the inverse of that question would be logarithmic. So what exponents on the number 5 would give you n. The reverse of that is the log of 5, and what number is this? So like how many times can you cut it into fifths before you get to 1? Obviously is log of n time. Again, if it feels like I'm going too fast, I know I'm going too fast, but I just want to get y'all a taste. So this example right here, looks like we're looping from 0 to n. And in the inner loop, we've got a logarithmic loop. So this is an example of n log m, right? Because the logarithmic operation happens, this is log time complexity, but it happens n times, therefore n log m. In this example right here, same idea pretty much. Nihar wanted to make a point that you actually need to make sure that the program can terminate when you're asked about the runtime, because this is an example of a program that will never terminate, because the condition right here is checking that j is less than or equal to m, but you're starting at 0. So you're just going to be multiplying 0 by 2, 0 by 2, 0 by 2, 0 by 2, forever and forever, and then you're never going to terminate. So this is technically like infinite running time. As far as conditional statements go, like if you have something like if log of n or else O of n, else O of n, you pick the worst one. So if you have a conditional and 2 different options for runtime, you pick the one that's worse. In this case, O of n is worse than log of n, so this thing overall has runtime O of n. This example is a little hard to understand. Basically, if you have an external function that has logarithmic time and then you run that n times, there's like a little derivation you can do right here. So I encourage any of y'all like tryhards to figure that out. And then same thing. So y'all tryhards, do example 9 and 10 on your own, see what you get. Credit to Nihar for these slides, you did a good job. Okay, any questions? That was big O review.
Do you think for this class we're gonna need to know how to write out the running time
Yes.
equation? Okay.
Yes, that'll show up on homework 1. And right now the TAs are still working on drafting up the problems for the first test. So I can't explicitly say what the problems are going to be because I haven't seen them yet. But if memory serves right, previous times we've done this class, there have been questions like you have this function, and then like you're counting assignments, allocations, operations, and whatnot, and it'll be like a multiple choice, and it'll actually ask you to do that math. So yes, you'll see it on the homework, like the written homework, and you'll probably see it on exams. You might see it in a quiz. So yes, I would be very, very comfortable solving this type of problem. Will it be something as difficult as this slide? Maybe, maybe not. I'm leaning on probably maybe not, but to just conceptually understand how do you get from point A to point B is important still. So good question.
And it hasn't been mentioned much, but homework 1, I'm guessing we should start it now.
Yeah, I would look at it. Yeah, I would definitely look at it. As far as the time that it's going to take to complete, I feel like the homeworks are definitely easier than the programming assignments are, but they're a lot more theoretical. They're a lot more concept based. So if you feel good on the concepts, the homework should be pretty fair, I think. But yes, I would take a look. Oh yeah, so that was big O. We're gonna move on to searching and sorting algorithms. So I'm gonna blow through these slides really fast because I actually coded up examples because I want y'all to see what these actually look like. So the first thing we're gonna talk about is linear search. So as kind of an addendum to the last PowerPoint that I went across, saying big O is kind of not the that's kind of not the full picture when you're describing the time complexity of an algorithm. So when you're describing the time complexity of an algorithm using big O, technically you're talking about the worst possible case. So if most of the cases are O of n, but there's one case where it's factorial, the big O is factorial. But within certain algorithms, you can say like, okay, well, if the input looks like this, or if the input looks like this, it's going to be more or less efficient. So big O describes worst case. As you can see, there's also best case and average case notation that specifically is going to give you like more detail on whatever algorithm it is that you're looking at. So for linear search, this is pretty easy. So for instance, a linear search would be like you have an array or some kind of iterable object, and you have a target that you're looking for. So in this example, let's say maybe you're looking for 23. In order to linear search this array, you're looking for your target, you have to iterate across all of the elements, right? So doesn't match target, doesn't match target, doesn't match target, and then boom, you found it. So the worst case would obviously be if the target was the last one. So if you're searching for 85 and the array is presented to you like this, you have to iterate across the whole thing, and that's the slowest that it would possibly take. Or if you're searching for something that doesn't exist in the array, like say you're looking for 42, then that's also worst case because 42 doesn't exist, and you would have to check every element to make sure that it doesn't exist. Best case is obviously you're looking for the element that's, just happens to be the first one. So if you're searching for 112, that's O of 1, whereas worst case is O of n. And then the average case is going to be, obviously your target is probably somewhere in the middle, but O of n squared O of n over 2 is still the order of magnitude linear time, so still a linear algorithm. Binary search is quite a bit more powerful, but you can only use binary search in a specific sub case of linear search. So if you're trying to linear search an array that is random, like you can see it's mixed, like it's not sorted at all, and that's your best bet. But if you're given an array that is sorted in ascending or descending order, then you can use that information to perform a more efficient search, right? So binary search, the name relates to binary is in like 2, right? So the name means that you're searching this side of the list and this side of the list at each iteration, right? So to perform a binary search, you look at the middle of the list. If your target is there, you stop. If it's not, then you know that if the target, like depending on the value of the middle element, if the target is less than the value of the middle element, now you don't need to look at any of these again, right? Because say your target is 10. You pick the middle element to look at, let's just say you pick 32. You will never have to look further in the array than 32 because you're looking for 10 and you know everything past 32 is going to be larger than 32 and is also larger than 10. So now you're just searching half of the array. And then you repeat that and you repeat that until you just have one element. And to give y'all some idea of how much better specifically binary searches over linear search is, like, like maybe you've heard me say, oh, this is log time complexity or this is linear time complexity. Like just saying those things doesn't really give you an idea of how big of a difference that is. So for instance, I pulled up this log base 2 calculator right here. So if we've got 10 elements in an array, so we're binary searching across 10 elements, then worst case, we're going to have to do 3 comparisons, I guess 3.3, so I guess technically 4 comparisons to find our element. If we have 100, then it's 6.6. If we've got 1,000, then it's 10. And what that's saying is, like, you can see asymptotically as the input gets bigger, linear search would be 1,000 comparisons and log search is 9 comparisons, right? Like you can see how this would become, like this would get out of hand very quickly. If we go to 1,000,000, so 1, 2, 3, now we're looking at 20 comparisons versus a million comparisons. So just if that gives you some kind of like ground to put your foot on, let's see, 1, 2, 3, it should be 30 comparisons for a billion entries. So 30 versus a billion, it's a big deal. So like when y'all see things like, oh, log of n versus n, this jump is huge. Like this jump is really, really big. And that's kind of maybe not explained so well by just seeing, oh, well, logarithmic must be better than O of n. Like when you see it this way, it's like, okay, well, obviously we're talking orders of magnitude here. So as far as binary search, there's an example in these slides, but the example, I don't think it does justice to the actual algorithm. So I coded up an example, and let's see. So I think y'all might have to do binary search at some point. So if you ever have to implement it in code, don't tell Lake that you saw it here first. Just keep that to yourselves, maybe. No, I'm totally joking. But okay, so this program right here is binary search. See, hold up. Yeah, so as you can see, obviously include IO stream using namespace std. I define binary search as this function right here, and then I've got a little main function. So as you can see, if we've got an input that is an array and it's sorted, and this is important, binary search only works if your array is in sorted value, if it's in sorted order already. If it's not in sorted order, binary search doesn't do you any good at all. So anyway, so we've got an array with 21 entries, 0 to 20, size of 21, and then we're going to be calling binary search. We're going to be looking for 14, we're going to be looking for 10, and we're going to be looking for 21. So 14 is a bad case, and you'll see why. It's a case that's not super efficient to look for 14. 10 is a good case because 10 is the middle element, so that's the best case, obviously. Whereas 14, we're going to have to jump around a bunch of times before we actually get there. And then as far as 21 goes, we won't be able to find it. So we'll have to do the maximum number of comparisons, and it still won't be there. So just a quick overview of what binary search looks like. Specifically for binary search, we have, it's a 3-pointer algorithm, essentially. So we're tracking the leftmost index of where our target might be, the rightmost index of where our target might be, and then we calculate in between those bounds, what are we looking at? So essentially, we've got a while loop right here. And as per my example, if array was size 1 billion, this while loop would happen 30 times. Or if it was size 1 million, it would happen 20 times. Or 1,000, it would happen 10 times, right? So essentially, at each iteration, we start with the left pointer being all the way at the left of the array, and the right pointer being all the way at the right of the array. We look at the middle element, and then if the middle element that we're looking at is the target that we're looking for, we return the target and we exit and we're good. Otherwise, if the element that we randomly picked happens to be less than the target, then we can move this left pointer up, right? Because if, say, for instance, we're looking for 14, then at the first iteration, the middle of the array that we pick is going to be 10, and 10 is less than 14. So we never need to look at any of these numbers ever again, right? So if the array of middle is less than the target, we never have to look at the size of the array again. And essentially, we're performing binary search on the next half of the list. And same thing for the right side, so on and so forth. And if we get to the end, this conditional will break when the left and the right are like right next to each other, essentially. We say you couldn't find it and then return false. So I'm going to go ahead and compile this. Equals plus 17. And I called this binary search. So as y'all can see, so as y'all can see, we found 14 at index 14, obviously. We found 10 at index 10, and we couldn't find 21. So these are these print statements right here. So we found 10, at index 10. We found 14 at index 14. We could not find 21 in the array because it wasn't there. And then I'm going to uncomment this print statement. So basically at each iteration, now it's going to be showing you the middle of the array that we're looking at. So it'll be 10, and then it'll be like, 15, and then whatever, bouncing until we find it. And this I wanted to give y'all some idea of when I was saying like earlier, best case, worst case, time complexity. As you can see, binary search is obviously log time. Like that's the whole point of showing y'all this algorithm. It's more efficient than linear time. But you can see depending on the input, when we're looking at 14, the target we're starting at, we split the list at 10, so now we're looking at this list, and then we split it at 15, so now we're looking here. And then as you can see, we split it at 12, so now we're looking here. And then we split it at 13, so now we're looking at this. And then we finally find 14 and we return it. But that right there, that was like what, 1, 2, 3, 4, 5 operations. That's significantly slower than if you happen to be searching for the element that is already in the middle, which you just find it and return immediately. So same algorithm, different efficiency based on a different input, right? So that'll be a theme that y'all just have to see as the course progresses. And then, obviously for finding 21, this is also worst case because, we start at 10 as our target, and then we cut the list in half, and then now we're looking at 15 to 20, and then we cut the list in half, and we're looking at 18 to 20, and then we look at 19 and 20, and we still haven't found it. And when you have a searching algorithm, and you can't find your target, that'll always be worst case. So as you can see, bad case, best case. This is also worst case because specifically you can't find it. And yeah, so that's binary search. Again, huge hint if y'all ever end up having to code binary search yourself. I don't know if you will or not. Any questions before I move on from searching to sorting?
And you said that that search only works with a sorted array.
Yes, yes.
Yeah.
So if you want to be technically very precise, binary search can work as long as there is like if you have like a rotated sorted array. So imagine you have like starting here, you've got like or actually I'll just show you in code. If you have something like oh oops, what did I do? Yeah, so if you had something like an array like int so long as you know that like the information that elements will always be ascending in one direction is really what you need. Let's call it 5 is equal to, imagine you had something like this. You could still perform binary search on something like this so long as it's like kind of sorted, but you'd have to jump through more hoops and you probably won't see it in this class. So that's like a leak code problem. But yes, essentially you need to be able to rely on the fact that like the reason you can cut the list in half, right? Like the reason that the binary operation works is because if you pick something in the middle and that you know that like for instance for target 14, if you know that you've picked something that's less than the target, everything to the left of this middle will always also be less than the target. So you never need to search this part of the list, which is why you can cut it in half. But that's a great question. And specifically when it comes to applications of binary search, I would say it's useful when you have a sorted array. And you might think, oh, that's like a super specific case. When would you ever see this? Like imagine you have a search space that is not an array, right? Like imagine you have a function where you can calculate the output of that function for a million numbers. Well, and like, if you're looking for a target of that function, instead of calculating it a million times, and then picking the one with the target, you can do binary search on a function, right? So instead of calling the function a million times and then looking for your target, you can call the function with the middle of your range of possible values and then so on and so forth. And instead of calling a function a million times, you can call it 20 times. But that's like a very advanced question. Excellent question to whoever asked. Yes, it is absolutely mandatory that the order is mostly sorted. If it's not, there's a trick to get around it. But for this class, yes, you have to see strictly sorted order in order to do binary search.
Since it's sorted and it's also like being split in half every time, it would also work well with recursion, right? We could do this recursively pretty
Yes, you could.
easily.
Yes. So I'm doing it iteratively in this example that I've got right here. But if you wanted to define it iteratively, I mean, if you wanted to define it recursively, you would essentially at each stop right here, you would define this is a breakpoint, and then instead of doing left is equal to mid plus 1, you would just call binary search, and instead of passing the original array, you would just pass this half of the array, or you would pass this half of the array. So yes, you could do it. You could do it recursively, absolutely. So, obviously if the midpoint is less than the target, then you can just pass the rightmost half of the array recursively, or you can pass the leftmost half of the array recursively. Great question. But I don't think you're going to see recursive. You might see recursive binary search, probably not though. Okay, so sorting algorithms. Obviously the noob sort is bubble sort. Y'all have probably seen this in lab or lecture. We got insertion sort and we got selection sort. Specifically on this little slide, I'm gonna show y'all maybe some patterns that you might notice. So bubble sort is the easiest one. It's also kind of like the noob sort. So let's look at this first. One of the characteristics of bubble sort is that the highest element will bubble to the last, or I guess in this case it'll be here and then here and then here. But the trick with bubble sort is that the highest element will always filter to its correct position at each iteration. So, obviously 9 is going to be the highest element here, and then 8 filters to its correct position, and then 7 filters to its correct position, and then 5 filters to its correct position, and then boom, it's sorted. Depending on how you implement bubble sort, it might actually have a different best case than the worst and average case. So in this code that's given right here, you have a little flag to check how many swaps happen. And if no swaps happen, then it breaks early, and that's, best case O of n. So imagine you were to call bubble sort on this array right here. Well, you would see 2 doesn't swap with 4, 4 doesn't swap with 5, 5 doesn't swap with 7, so on and so forth. 0 swaps, you would terminate early, and then you only did n comparisons, so it would be O of n. Worst case, however, is somewhere more like this, where you're going to have to, for each comparison, for each element, in order to filter it to its position, you're going to have to do n comparisons. You can think of selection sort kind of as like in function, almost the exact opposite of bubble sort, where instead of the largest element always finding its correct position at the end of each iteration, it's the lowest element finds its correct position at the end of each iteration. So obviously you find the minimum from the list, put it here, find the minimum from the remainder of the list, which in this case is 2, put it here. And then as you can see, the pattern here is that we've got a growing sorted list on the left side, and that's selection sort. So if you see a test question and it's like, you don't get like this information right here, you just get like this chunk. You just get this chunk of numbers. For bubble sort, you're looking for a sorted sublist starting from the right side. For selection sort, you're looking for a sorted sublist starting from the left side, if that makes sense. And then insertion sort is a little bit more tricky. Essentially, you're going to be seeing a sorted sublist starting from the left side, but instead of finding the minimum element at each iteration, you're just finding whatever would maintain sorted order in the sorted subarray on the left. So again, difference being that for selection sort, you'll see the sorted subarray growing from the left side, but also you'll see the minimum element here. Whereas with insertion sort, you're seeing the sorted subarray growing from the left side, but you might not necessarily see the minimum here yet. So that's how you tell the difference. For insertion sort, you're doing comparisons backwards. So this is the sorted subarray, and then to add 4 to the sorted subarray, you compare 4 and 3. And then you add 1 and you compare 1 to 4, 1 to 3, put it in its right place. I think insertion sort is kind of like, for anyone who's played cards before, it's if you've got like a hand of cards in your hand, and you want to sort the cards and find the right position, you have like a sorted part in your hand and then an unsorted, and then for each card you just compare and put it where it needs to go and put it where it needs to go. Before we run out of time, I do have coded examples of what all of these look like as well. I might have to blow through these. So this is what bubble sort looks like. I've defined this little function right here. So print array takes an array of size and prints out the values. I've got a main function. I've got, these obviously unsorted values, some size of the array. And then it's going to print what the array looks like before bubble sort. It's going to call bubble sort on that array, and then it's going to print what it looks like after bubble sort. And as you can see, so basically what happens here is you start at the 0th element and you iterate. In this case, it would be n times, or size minus 1 times. And then for each iteration, you start at the first one and you do comparisons until you get to size minus I minus 1. And what that looks like is, let me see. So the first iteration, you're going to go all the way here, and you're going to do swaps until you have this element filtered. For the second iteration, you don't have to iterate and compare with this last element, because for each iteration, you know this last element has reached its correct position, and then you're going to iterate to here because you know these two elements have reached the correct position, and then you're going to iterate here. If that makes sense. So hopefully I'll find a place to post this code so that y'all can see it working for yourselves, but I'm going to go ahead and compile this and run. So I called this bubble sort, I think. Yeah, that's right. Okay, yeah. So as you can see, it works. That's proof. You know, it's sorted. And essentially what you're saying is you're tracking this index J, and every time you have an element on the left that is bigger than an element on the right, you swap the two. STD swap is just shorthand for swapping two elements. Otherwise, you would have to create a temporary variable and kind of like do a juggle a little bit. This is just a little bit easier. For selection sort, it's something similar. So same skeleton code as the last one, except, you know, different, obviously unsorted array. These numbers are not in sorted order, totally random. I didn't choose them for any reason whatsoever. And then for n times, you're going to find the minimum element from the array n times. So finding the minimum element is O of n, and that happens n times. So, you know, again, it's O of n squared. So essentially, minimum is just the index of the lowest element, and you're initializing that to I. And then for each pass, you're going to be computing the new minimum element and then swapping that element to its position where it needs to go. And again, if it feels like I'm going at light speed, I am in fact going at light speed. This is way too fast, but just remember, for selection sort, you find the minimum and you put it at the first index, and then you know that the minimum is here. So now you're searching through this part of the list, and then you're searching through this part of the list, and through this part of the list, and then through this part of the list, and then through here, which is why the terminal case for this loop looks the way it does. So, you know, obviously you need to do the outer loop n times because you need to find the minimum n times. But for each iteration, you're starting at the 0th element, and then you're starting at the first element, and then the second element, all the way through the end. So this loop condition right here is what I was talking about. So you're looking here, and then here, and then here, and then here. And the way that looks programmatically in code is this condition. So you're ending at your starting J is equal to I, because you know everything before I is already sorted. And then essentially after you found the minimum at each pass, you swap the array that has the minimum element and then whatever the sorted position it should be. So if I go ahead and run this code, I called this what? Selection sort. See. And as you can see, we start with this input, and then by the end, it's completely sorted. You know, surprise, surprise, is what it looks like. And yeah, I really need to find a place to post this code somewhere so that y'all can see what it looks like. You know, I just thought, like, when I took this class and I had to look at you know shit like this, and I couldn't see it actually working. It just didn't really help that much. But anyways, we got one more. We got insertion sort, which is right here. So again, same skeleton code, print array, and then we've got some array of, you know, obviously unsorted material, and then we're going to call insertion sort on it and see what happens. I think insertion sort is like conceptually the most complicated one to see what's happening. So essentially in this example, we are starting at I equals 1 instead of I equals 0, and then looping through size for the outer loop, the first iteration. So that's like essentially saying we don't need to start at 0, because we know that the first element will, like, you know how insertion sort, we're maintaining a sorted sub array at each iteration, and then whatever is the closest element to that sorted sub array. So in this case, we'd be looking at 7. We're just finding where 7 belongs in the sorted sub array. We start the sorted sub array at 4, and there's nothing to compare 4 to, so we don't need to iterate here. So essentially, I'm like skipping this step, if that makes sense. And then, you know, we're comparing 3 to 4, and then we're comparing 1 to 3 and 4, and then 9 to the list, and then 7 to the list, and then 2, and then by the end it's sorted. And the way that that looks in code is right here. So, you know, obviously I explained why this loop is the way that it is. And essentially the current tracks whatever elements of the array is on the outside of the sorted subarray, and then you move that element to where it needs to be using swap, and then you de-increment cur each time. So essentially what that's saying is that, like, for this iteration, cur would be 1, right? So this would be I equals 1, so we'd be looking at this element. This is like starting from 0 index. This is the 1th element, or this is the second element right here. So if this is the sorted subarray at this iteration, we're looking at 1, and we're comparing 1 to 4. And while this is less than this, we make a swap, and then we make another swap, and then it's in the right place. And then that'll happen until the array is totally sorted. So I'm gonna go ahead and run this. So I think I called this insertion sort. Let's see. Yeah, and as you can see, we take this completely unsorted input, and by the end, it's completely sorted. And then I made this comment right here. So if you want to see like what's actually happening, on this, yeah. So at each iteration, I'm printing the array to see what it looks like. So as you can see with this example, we've got 4, and then we're swapping 3 and 4, and then we're swapping 2 and 3. I mean, I guess it would be 4 here, 2 and 4, and so on and so forth. And that's displayed down here. So we're calling it on, this is what the input looks like at the first pass, and then we swap 3 and 4, and then, you know, we need to find where 2 belongs, so 2 goes here, and then we need to find where 5 belongs, so 5 goes here, and then we need to find where 1 belongs, so 1 goes there. Essentially, if that makes sense. And if I had, from this slide, if I had just copied 431972, which actually I'll do just for giggles. See, it was 431972. I'm gonna go ahead, like, I'm gonna copy that to my clipboard, and then if I paste that here, it should give us the same exact order that we see in the slides. So and then, yeah, so this hopefully I think is the exact same order that we see in the slides. Yeah, I think so. So yeah, I'll find a place to post this code somewhere if y'all want to dig through these and just really get an understanding of how the different searching and sorting algorithms work. Next week I'm going to be going over some different algorithms, but these are kind of like the basic sorts. You know, I didn't implement linear search. I trust all of y'all to be able to do linear search yourself, but this is binary search. You know, this is a good foundation for starting to learn how to search and sort things. Okay. So anyone have any questions whatsoever?
I guess when you have like this is for big O notation and like functions and stuff, but like when you're like initializing a variable or you're returning a specific variable, like are each of those like O of 1 would each of those be O of 1?
Yes. Mhm.
Okay.
Yeah, anytime you have like a operation that involves memory, so if you're doing an access, so like or an assignment, yeah, that would count as O as 1, O of 1, because I guess like technically finding the location in memory and then setting something else in memory is like, I guess, a little bit expensive, so that'll have the same cost as doing like, you know, 1 plus 1 or some kind of math. Good question though. That's a good question. Anybody else? Nothing. Okay, well, if you think of questions, shoot me an email. I'll probably make an announcement where I'm posting the recordings slash I really ought to make a GitHub for the sample code so that y'all can dig through it. I haven't done that yet, so I should keep my mouth shut until that actually happens. But without further ado, y'all go have a great rest of your 3-day weekend. If you're here on a 3-day weekend, I respect the grind incredibly. Y'all are all going to be super successful in this class. Let's see. Someone says, can I post the recording to Discord? Yeah, I'll try. I'll figure it out. Probably. Yeah, something like that. But again, thank y'all for showing up. The grind is immense amongst y'all.
Thank you.
Yes, of course, of course.